I also honored that today with us a special guest, a brave man, Mr. Olivier HOUZE, 2025 SPE International President. Let's imagine that international person also here with us to support SPE society in Ukraine and to assist all Ukrainians to continue be brave and to develop our oil and gas activity. Mr. Olivier, you're welcome to your presentation and some words. Thank you so much.
Well, thank you. So can we start my presentation? So one thing is that if you are online, you may not be able to see my manual laser pointer. So I mean, the students know it already. So what I say is that in 1 month's time, you will not remember what I said, but you will remember the laser pointer. Sorry for the guys online. I think that you are not going to enjoy the, let's say, all the spectacle. But anyway, you just, yeah, but it's, okay. You're already giving away too much. Let's see, here we go. Yes. All right. So, okay, so I'm going to have, so the thing is, no, I have only two hands. So I guess I will let you just say next, okay? Yeah, so what I wanted to do in this presentation was to speak about a few things that I guess are key, especially for our young professionals and students, especially related to energy transition. So next. So as a personal introduction, so I have to confess. So again, students, you already saw this introduction, but after that, it's going to be different. I have to confess that I decided to join the industry after watching this 1968 John Wayne movie, where the main character was inspired by Red Dead, you know, the flying fireman. And I thought it was really cool, and I said, this is the industry I want to join. And then I got a scholarship to go to Stanford University to learn about petroleum engineering. And I had two big disappointments. The first one is that I thought that oil and gas was stored in caves, and you just need to get a hole and get it. And no, there was this thing called Darcy's Law, you know, and so for the reservoir engineers, which was making things much too complicated. And the second thing was that the normal process was not to drill a well until you reach the oil, then you have a blowout, then you call Red Dead, it fixes it, and then you start production. That actually the goal was to avoid that. But anyway, it was too late to change my major, and my history was set. Next. Now, so this was my, my expectation. The reality was actually better than my expectation. And as an illustration, these are pictures that I took, that were taken last month when I visited French-speaking African countries. And, you know, let's say the energy that you can see by going around, visiting sections, visiting student chapter is great. It's even much greater than being John Wayne, you know. So next. But this personal introduction to say that when I joined the industry in 1983, it was a relatively easy decision. What I mean is that you could love it, you could hate it, but there was no issue with climate change. So you had the thing about peak oil, but peak oil was something that seemed to be moving 10 years, every 10 years, so that was okay. So you only had positive reasons, you know, the technical challenge, the personal challenge, travel, good money, John Wayne thing, so everything was positive. It was easy. In fact, you could be a kid and say, I want to be there. Next. Joining the industry today has to be a qualified decision. In other words, a student that considers joining our industry, or young professionals that consider staying with our industry, has to answer two questions. One that is a selfish one, which is there a career for me? And one thing is that, you know, a lot of people say, you know, we have at least 20 years of oil and gas. Yes, but I'm 25, 20 years, that's 45. How about after? Will I be obsolete? So that's one question, the selfish question. And then there is the altruistic question, which is, am I on the right side of history? Okay, am I a bad person if I join the oil and gas industry? And naturally, if I'm here, my answer is yes and yes. But the thing is that it is an answer that you have to provide to yourself. Nobody decides to answer on your behalf. So you need to kind of have a qualified guess and answer to this question to decide if you join us. And as you can see, as you can guess, a lot of this answer is related to energy transition. Next. Okay, next. Okay, so first of all, SPE, and this is something, you know, SPE, we are Society of Petroleum Engineers, but we have, technically it is a 501c3, not-for-profit organization, but the short story is we are not expected to lobby. It is not us, it's not SPE that says we should have more oil and gas. This is not our business. Our business is to provide the energy that are asked by our society. If our society say, you have to close shop, we close shop. SPE is not here to make lobby. But in any case, we need to have a sort of P50 for those who are familiar with reserve. So this means that we need to have a cold look at what is happening so that we can tell our young professionals, our students, you can join the industry because this and that. But you know, when I joined the board and I came back and I started traveling as SPE president, I was stunned to see how different energy transition is perceived depending on where you are. Like the first trip I had was in Amsterdam, and there was a young professional that told me, oh, could you please remove the P from SPE because petroleum, it's killing us in Europe, okay? And then almost, let's say 1 week later, I visited the Caspian, you know, Kazakhstan, Azerbaijan. And then I visited the main companies, you know, KMG, SOCAR, etc. And they told me, you know, well, yeah, net zero, yeah, 2060, 2070. But right now, our priority is to invest so that we are going to produce to a plateau in the 20 to 30 years to come. Not the same story. And then I went to Argentina. In Argentina, you have the development of unconventional, it's called vaca muerta. And it's getting to the point where Argentina had a conventional production that peaked in 2005, then it went down. With the unconventional, next year they are going to beat their historic record and go on, go on, go on. It's getting to the point where Argentina was importing gas from Bolivia, and now they are using the same pipeline to export back to Bolivia. So in Argentina, the sky is the limit. Now, if I go, for example, to the United Arab Emirates, you take ADNOC. I visited ADNOC several times, and they would tell me one thing. Come to this island, you will see this farm of solar panel. They're investing billions and billions of dollars in new energy, in energy transition. But at the same time, they say, we will be the one to produce the last barrel of oil on Earth. Okay, so in other words, they are using oil and gas to finance energy transition. So as you can see, the story is very different, and it's strange because we are on the same planet. So how is it possible that you can have all these different stories while actually we are facing the same challenge together? So this is actually, you know, you may have seen that, you know, these are the different scenarios from the IEA, you know, International Energy Agency. And so, and of course, you can imagine this is a scenario in terms of emission of CO2. You can imagine, so the steps corresponds to what countries have agreed during the Paris Agreement in 2016. The other one is, if you believe politicians, if you believe everything they say, that's where we would go. And net zero is a kind of a technical constraint to say we will be net zero in 2050. You can imagine that depending on the scenario we will follow, our license to operate is going to be very different. So next. Now, you could consider, you know, I don't know if you know where the term energy transition comes from. No, so I saw that it was coming from I don't know, NGO or maybe some government agency or UNO or whatever. No, the term energy transition is coming from lobbying in the US in the 1950s of the nuclear energy, the nuclear industry. And the idea was to say, okay, so there was some paper done by King Hubbert, who was actually a shale geologist, saying that essentially we would reach a peak that was not related to climate change. It was related to the identification at the time that we had a limited amount of oil and gas. So the idea was to say, we are going to have a peak, and to replace this peak, we need to have, let me just shorten a bit my, okay? You will need to have something to take over. And the idea was to say, please invest massively in this new generation of nuclear power plants. And this will allow to replace the oil and gas forever. They had even this thing where you would have thousands of years, and it would show that oil and gas was a sort of necessary blip in the history of mankind before nuclear energy takes over forever. So again, the term energy transition is, so after that, it was taken over 20 years later in the context of climate change, but at the origin, it was a US lobbying by the nuclear industry. Next. So now, if you consider what the IPCC says, you know, essentially the official statement related to energy transition is that we had energy transition in the past when we moved from wood to coal or from coal to oil and gas. And the idea here is that the energy transition that we are going to do in the decades to come and to replace oil and gas by something else, we did it in the past, but faster. And as an illustration, they show this graph, so, which is exact numbers of the the transition between wood and coal in the 1800 above on over 140 years, okay, or the transition between coal and oil and gas over 50 years in the 1950s. So you could say, okay, there is a replacement, but actually it is very misleading because this is in percentage of energy, not, and so it doesn't take into account the increase of energy production. If you look at that next, the story is very different because in fact, what you see here is that if you take wood, if you take coal, if you take oil and gas, the energy transition has never been about replacing an energy by the other. It has actually been by aggregation. The new energy would take over the growth, while the old energy, you can see the peak of coal was not in 1920 when oil started. The peak of coal was last year until next year. So you can see that mankind has never reduced in its history its consumption of any sort of energy except one. You may, okay, I will not ask you because this is tricky. The only source of energy that was replaced was whale oil. Whale oil was replaced by oil and gas in the 1920s. It's good we stop killing whales, but this is actually the only source of energy that has gone down. The others have always gone up. And even here, I don't show animal muscular energy up, human muscular energy up. So we have never gone down. So it doesn't mean that we should not do it. But if we do it, if we replace oil and gas by something else, this will be the first time it ever happens. Okay? So we have to take into account this sort of historical fact when we say the energy transition that we are going to have is the same as we did. No. We never reduced any energy in the past. So that would be the first time. Next. And let me just illustrate also how historically old energies have been used to deploy new energies. So that's an example here. So this is a picture of the main Ford T factory in the US in the 1930s. And you can see that half, I mean, it's not very clear, but half of the area in the factory itself, half of the area is minerals, and the biggest mineral is coal. Why? Because in 1930s, to build one Ford T, you needed 7 tons of coal, which would be more coal in weight than the weight of gas that the Ford T would use in its life. And today, to build an electric car in China, you need 2 tons of coal still. Next, wood. You know, so this is a picture of a coal mine in the 1830s. No, 1930s, sorry, yeah, whatever it was. Yeah, no, in between. You know, so wood was replaced by coal in terms of basic energy, but because of the amount of wood that was needed for the infrastructure, in fact, the consumption of the UK of wood was 6 times, in 1930, was 6 times the consumption in 1830 when wood was the main source of energy. So in other words, wood was used to develop coal. Now, if you go next, now if you go today with the current energy transition, you know that we to electrify transportation, we need coal, we need copper, and we need lithium. Now, the largest producer of lithium and copper, at least one of the largest, is Chile. And where do you find the copper and the lithium? In the desert. So take and you know to produce 1 ton of copper, you need 90 tons of water. To produce 1 ton of lithium, you need 2,000 tons of water. How do you take these waters? So sometimes you can get water from the Andes, but actually, in most cases, what you will have is that you will go to the ocean, you will put a desalination plant, you will create 150 kilometers of pipeline, push the thing up 2,000 meters, and that's how you are going to produce copper and lithium. In other words, you need coal, you need oil, you need gas, etc. So just to say that the reality today of energy, the energy is very mixed. And so this means that you would need actually to increase your consumption on the old one in order to develop the new one. Next. So if we look at the different scenarios, not in terms of CO2 that I've shown before, but in terms of oil and gas, you see that out of the different scenarios, there is only one, which is a step scenario, which is kind of considering that there will be a plateau of oil and gas in the decades to come. And honestly, and if you look at, let's say, again, the past history of energy transition that I've been showing about the current rate of transition, you know very well, you know, you can see how much we are consuming now. And also the fact that emerging countries need cheap energy, and emerging countries are not going to sacrifice their growth to pay climate debts that they have not contracted. So everything pushes, for the time being, towards the step scenario. So the step scenario is what we seem to be following. And what is interesting with the step scenario is that you have actually, you know, the thing that I was saying is so different depending on where you are. You can see clearly that the developed countries are going to reduce their consumption of oil and gas, which is logical, but it will be compensated by the need of emerging countries. So essentially, so again, I don't say it's a good or a bad thing. It doesn't mean that we should not do more. Maybe, let's say, if the climate crisis speeds up, we may have to do something. But currently, this is where the trajectory we are following. And as an illustration, you know, I was at the IEA, International Energy Agency, which is based in Paris, a couple of months ago. And when I visited them, you know, I was wondering why they wanted to see me. And actually, it was to discuss about a certain number of common projects related to geothermal, related to carbon storage, reserves, etc. So in other words, agencies that used to say, oh, we are on the wrong side of history, are changing a bit and considering that indeed now, if we want to solve the problem in a realistic way, we need to be involved, basically. Next. So what does it mean for SPE? And this is a paradox, because of course, energy transition is a challenge to our license to operate, that's for sure. But in terms of our technical perimeter, it is not a reduction of our technical perimeter, it is an extension of our technical perimeter. Because beyond what I call the core activity, essentially oil and gas, now we have two classes of additional activities that we have inherited from the energy transition. The first one is what we call low carbon, which includes the reduction of emissions. Let's say our industry, as all the other industries, have to do we have to do our homework. We need to check whenever we waste and we are creating emission of CO2 and methane, we need to reduce it, which is a challenge, especially for methane. But also we have negative emission with carbon storage. And then we have what we call new energy. Now, not new energy at large. We don't have anything to bring in terms of solar or wind or whatever. But whenever we are subsurface, whenever there is diffusion of fluid, this is our territory. So whenever there are some energies that is related to that, and especially geothermal, this is where we can bring something to the table. And this also adds some kind of hydrogen, some storage, critical minerals, etc. So that's the paradox, is that the energy transition for us means more work, not less. Next. So again, as a conclusion, so the step scenario seems to be our current trajectory. We see that we will effectively have a stable oil and gas in the 20 years to come, probably beyond that, even though we can anticipate that we will go down a bit. But we have two activities related to low carbon and new subsurface new energy that is added to our to-do list. In other words, young professionals or students, if you join our industry, it is very likely that at a point, and this may be different.
So, dear colleagues, maybe as I understood, now is air alarm. Please, everyone go quickly as possible to the bomb shelter, please. And after finishing, we come back and continue. Thank you.
All right. So I'm finished
Thank
with
you, first of all. Mr. Olivier, thank you so much. You will be able to discuss internally, privately, this all our colleagues in a nice and suitable bomb shelter and presentation, and our unique expert. And I'm pleased to introduce our SLB and Detect on Gas speakers. Ms. Clairet Guerra, Senior Geomechanics Product Analyst, and Mr. Robert Derda, Senior Geomechanics Engineer. So thank you so much that you have found the time to join our SPE workshop. Thank you very much for your good job and your system. Welcome to your presentation. We are hearing to you very carefully. Thank you so much.
Thank you. So please let me know. I can't share my screen. If someone can enable it, please.
Yeah, just a minute. So colleagues who are flying our technical guys. Thank you so much.
Let me know when I can retry.
Correct. Please try once again. The green button.
Yep, it seems to be working. Yep, seems to be working. So please let me know what you can see or what you can you not see. So
1 second.
you can see yourselves.
Like it says double click to enter full screen mode. So we see something, but it's a black screen. So please try. Yes, we can see a screen.
Great. Yeah.
Okay. So now you can see yourselves. I'm moving you from the side, and let me know if you can pick up on the slides.
Yes, we can see.
Excellent. And now setting it up for presentation mode. And just let me know that you can hear me and see this properly.
Great. Excellent.
Okay.
You can start.
So thank you so much for coming back, first of all. I really hope that you're all safe. And thank you so much to the organizers for having us in this session. My name is Clairet Guerra, and I am the Geomechanics Product Analyst in SLB. And I'm presenting today with Robert Derda, Senior Geomechanics Engineer, with a lot of activity and connections in the Ukrainian side and this region of the world. So we have a compliance slide to show. We don't have to explain anything behind it, just so that you know, and to the logistics and the organizers, that this is encouraged by SLB, just to make sure that we don't incur in any legal breaks. So the world of geomechanics implies that one of our key missions is to understand what will happen with our assets once we start disturbing it, once we start drilling, injecting, or producing hydrocarbons, injecting CO2, and how our assets are going to react to those perturbations. There are three building blocks that we need to understand, and these are fluid pressure, mechanical properties, and rock stresses. And there are many levels that we can address this information, mainly from measurements taken directly through the drilling experience, and later on through modeling when we start analyzing the interactions and the interplay of these different blocks. Now, understanding these bits and how they react and interact with each other and with operations can be the turning point between a success story or a failure, as Olivier was given in his examples. We need to understand that we will enter the subsurface with some awareness, and we need to leverage the different domains that are participating in this analysis, mainly the geological setup. We need to understand what kind of formations we're dealing with, what kind of lithologies, as the origin of those formations will likely impact the behavior and will condition how the rocks will react to the different types of perturbations. There is an image that we can already create by means of different types of data, mainly well logging data. And the key input data that you need to remember is compressional slowness, shear slowness, and bulk density. And this is normally collected by means of acoustic logging acquisition. Bulk density, gamma ray, and calipers will also support the description of the stratigraphic column and the mechanical behavior along the wellbore trajectory. With very simple equations and with very simple analytical setup, we can already estimate the elastic and strength properties of our materials. We can assume or infer, depending on the geological context, and apply some empirical models to draw the pore pressure profiles. And with all of this information, derive a stress model. All of this based on assumptions, empirical equations, and a minimal modeling. All of this is a pure inference of what could be happening. Now, we also need to tie all of this information to the reality and what's actually happening. And this often comes from different types of calibration data. Mainly, we rely on core testing, but this is quite prone to human error. We also need to bring in the uncertainty on sample testing into our analysis. Pressure tests that will help us fit and tie the pressure analysis that we've performed, depending on the targets. Leak-off test, extended leak-off test, and different types of fracture tests that can help us tie in with a lot of confidence the minimum horizontal stress and different types of additional information like borehole images, calipers, and drilling observations that will help us tune in maximum horizontal stress and different properties to address the wellbore stability models. Once we have collected all this information, we want to start doing some analysis. And if we are working on the wellbore scale, we will refer to as wellbore stability models. And this can have different levels of reliability depending on the domains that we're dealing with. It can be a simple pore pressure and fracture gradient, or not only those hydraulic boundaries, but also mechanical boundaries like shear failure and tensile failure. And the key idea of a wellbore stability model is that you're able to collect and compile the offset data information, understand what's the mud weight window trend across your wells, and then validate this information and use it towards planning the future operations. We are mainly tracking, can you see my mouse? Can you see the mouse? Let me get the highlighter.
Yes.
Let me get
small,
the laser point. Yeah, here it is. So
Laser is better.
we're tracking different types of failure around the wellbore, and what we want to understand is how has been the experience in the different wells that have been drilled, and how do we map that in any further operation. We do encourage the capture of the uncertainty across all the modeling stages, because all the data, as you see, may be prone to error when analyzing or manipulating a sample. So when validating the wellbore stability models, we also want to capture the total or the field awareness of the measurements that have been collected. And we can do that by means of stress inversion, where we try to back calculate the onset of the occurrence of those measurements in an iterative loop, and mainly when you're working with a method called the poroelastic approach that helps you validate this process more efficiently. And you can do it in a multi-well type of analysis, so that you have the well resolution, but also the field awareness of your asset. Also, we want to understand how the logging data varies across the field with the different well data that we have collected. And we can do this by means of stochastic wellbore analysis, not only considering the uncertainty of the logs, but also of the measurements, and be able to address worst case scenarios, best case scenarios, and likelihood of occurrence. One bit that we need to pay attention at this stage is that we are going to have also instabilities due to heavily layered sections, and we can address this by means of weak plane analysis, not only as a formation along the well, but also depending on the orientation by means of single depth analysis. Once we have the awareness of the wellbore at the wellbore scale, we want to leverage all the subsurface work that has been executed and at reservoir scale, static modeling scale, or different types of interpretation, and make an assumption of what's the current state of that asset in the subsurface. And for that, we work with 3D mechanical earth models. Now, there is a process that tries to maximize that you take advantage of that data that already exists. And ultimately, the idea is to understand how, in connection with the fluid flow simulations, it will impact the safety and the integrity of your asset. One key bit that you can achieve with the 3D geomechanical simulations is tracking at cellular level. So this is a numerical model now, is tracking at the different cells what is the progression of integrity of that grid cell, whether you are still in the safe side or you are starting to fail, and what could be the implications of that failure. Also, you can work your way through wellbore stability and understand the direct impact on the wellbore with respect to discontinuities. Also, highlighting the value of uncertainty, you want to be able to work with scenario-based type of analysis, where you can also address best case scenarios, worst case scenarios, and likelihood of occurrence, but also identify in various stages of modeling what are those regions that are more prone to risk. Overall, we advocate for more holistic type of modeling that leverages all this information, multiple domains, and that you take advantage of all the information that it's available for your asset to understand the risks associated to your asset and ultimately bring it to safety, and that it is a success case. Some of the type of applications that you will directly use this type of modeling towards, it would be things like fault reactivation, completion integrity, different levels of wellbore stability, and depending on which domain you're sending the information to. On field scale, solid production, so sand production is something that can use this as direct input, subsidence or surface heave, depending if you are injecting or producing, and use all of this to optimize and enhance your stimulation. So here we switch. And Rob, maybe you can ask for control.
Yes.
If possible.
Let me do that. Yeah. I don't seem to have a...
I can transfer for you. Just say next.
Yes.
Yeah.
Let me see if I can share my screen.
Okay, that would also work. So I'll stop sharing now. And you can see
no.
my giant face.
I don't seem to be able to request and share.
No, you can just hit on share screen, and now you can probably move the screen to the side. Keep the presentation in the back. Yeah.
Can you see my screen?
Yes, perfect.
Okay, so let me make it full screen and swap the displays.
Swap, yeah.
Yes. So thank you, Clairet. So Clairet explained the background information and the background of the creating geomechanical model and its general applications. Now I will go through few examples of applications for drilling optimization and for the hydraulic stimulation. So the 3D geomechanical model allows us to to account for the impact of the structure on the stresses, as well as the influence of the presence of the faults and potential influence of the pressure changes in the reservoir related to either the production or the injection. Having the 3D geomechanical model, we can then compute a mud weight window for cubes for the different well deviation and the well azimuth scenarios. For instance, a vertical well scenario or horizontal well scenario oriented in this or that direction. And that can serve on the early stage of the screening for the planning of the future wells, identifying the zones that are safer to drill or more difficult to drill. Then we can also easily evaluate the mud weight window, so the wellbore stability, along different trajectories for the planned wells, right, across the field. So here we can see the example below of such a extract from the 3D geomechanical model, showing in the background the stress tensor, so the stress direction as a lines that are not very visible here, and the stress magnitude as a color, and the faults, right, present in the area. We also see the two wells that are located in the different parts of this structure and drilled to the different directions, right? So here you see on this trajectory is represented. This is the mud weight window extracted, evaluated for this trajectory, and the one on the right corresponds to this trajectory, right? So we can see on this example the difference on the mud weight window between these two trajectories, with the trajectory, this trajectory, having the wider stable drilling window that is represented here by the white color width, that basically means the stable hole, compared to the trajectory that is drilled in this direction, that shows a generally narrower window. And we also can see here indicated by pink lines the faults that are crossed by these trajectories, and also the impact of these faults on the mud weight window. So now I will move to actual case studies, two case studies that we will go through. So first, this is on the left, you can see the case study from Kuwait. That is the field with several vertically stacked reservoirs that are separated by shales. And this reservoir was produced for over 6 decades. And in this field, there was also a history of the significant hole instability and drilling difficulties. So what we see here on the top, it's the result from the dynamic model, reservoir model, showing the changes of the pore pressure over the time, right, as the operation in the field proceed. And that includes both the effect of the depletion with the purple color and the effect of the injection with the red color, right? On the bottom, we see the result of the 3D modeling showing the corresponding impact on the changes on the minimum horizontal stress magnitude, right? Where we also see the changes in the stress that are a consequence of these changes in the reservoir pressure, right? The plan for the development of this field was to drill horizontal wells targeting different reservoir horizons to optimize the production. On the left here, we see the wellbore stability analyzed for the initially planned well that you can see here. That shows no stable drilling window across the depleted reservoir. So we see here the low mud loss gradient, that is light blue, and the low breakdown gradient, that is the pink color, right? So that indicates the high risk of the severe to total losses. And at the same time, some gains cannot be excluded in case some zones are not depleted. And at the same time, we expect hole instability in the shales, right? So in this study, the well trajectory was actually slightly adjusted. Its position was shifted, and that allowed actually to find the better optimized trajectory to drill that you can see here on the right. That although shows a narrow stable window, nevertheless it shows the window that it's safer to drill, right? So it helped to optimize the trajectory for the safer drilling. On the right side, we see the case study from the North Sea. That's the Cook field. That is represented by highly deviated reservoir overlain by the overpressure shale. In this project, the plan was to actually, in this field, to drill the 2 wells, producer and the injector, to enhance production. On the right, you can see again the results of the wellbore stability analysis for these 2 well trajectories. As previously, we can see very narrow or no stable drilling window through the depleted zones that can again lead to the significant risk of the losses and the hole instability through the overpressured shales. And in this study, the geomechanical model was used to optimize the selection of the mud weight window to drill these wells with. As well, it was used to provide the input for the wellbore strengthening design. Additionally, there was also a further study analysis performed for the risk of potential sanding, right, in this study. So both wells were drilled successfully, and the production results exceeded the expectation in the consequence of this, advanced drilling engineering planning, including optimization of the mud weight window and the wellbore strengthening design. So now we'll move to the example of the application for the hydraulic fracturing. So geomechanics provides a critical input for hydraulic fracturing, and that includes stress direction, the stress magnitudes, and the elastic properties. The stress direction is important, especially for the horizontal wells, deviated horizontal wells, where depending how the well is located with respect to the stress, we can either generate hydraulic fractures that will be transverse to our well, or we can generate one longitudinal fracture along the well, right? Or something in between. Then another aspect, very important aspect for the hydraulic fracturing, is the both vertical and lateral stress heterogeneity. So that has the impact on the hydraulic fracturing design, on the completion design, selection of the stages, packers position, and perforations, and especially important for the horizontal wells. Again, critical for the selecting optimum zone to land the well, and then to select the optimum zones for the stages, for the initiating the fracture, and then for the optimized growth of the fracture in the structure. On the right, you see the example of from the Eagle Ford. So that shows the example of the 2 horizontal wells with the hydraulic fractures stimulated result that you can see here. And we can see in the background the initial background reservoir pressure and initial background stress direction and the stress magnitude condition. Now, in this stage, we see the impact of the stimulation. So we do see the net pressure during hydraulic stimulation. And then we can see on the right the consequence of that in terms of the change in the stress direction and the change in the stress magnitude that is represented by the color. So the yellow-red color indicates the higher stress magnitude, whereas these lines represent the stress direction. Then in the next step, we see the effect of the initial production with the reservoir pressure depletion simulated, right? And then on the right side, we see then again the impact of these changes in the reservoir on the stress direction and the stress magnitude. Now we see mostly the stress reduction. And here we see further effect of the further depletion during the later stage of the production. And we see, of course, the more significant impact of these changes on the both stress magnitude and stress direction. So this one, of course, has an important implication both for production, since with these changes in the stresses resulting from the depletion, there may be a drop in the fracture aperture and consequently permeability and then the production. But it also has the implication for the further well drilling, the infill well drilling. So to select the optimum position of these wells, to avoid the difficulties from drilling, because these changes, of course, can impact the mud weight window. And then also avoid potentially either drawing the fracture into already stimulated zone if we already produced and we locate this well too close, or not stimulating effectively this zone if we drill the well before production, but after we stimulated the previous well, right? Then we may have some stress shadow effect. And if we place the well too close, we lose the energy and not optimally create the fracture geometry as we would like to and stimulate optimally the area, right? So this is just the key short examples that I wanted to show of the application of the geomechanics. Of course, in these examples, we focus on the 3D application. Some of course, these applications, but not all. Of course, we can perform with the 1D as well in terms of the providing input for the hydraulic stimulation and for the drilling optimization. So this is all from my side, and thank you for your time and attention.
Excellent. Dear colleagues, thank you so much. Thank you so much, Ms. Clairet, Mr. Robert. Very simply, very deeply, and very understandable. Few moments from my side, as now not only SPE member, but representative of the tech oil and gas as a leader of innovation and private oil and gas sector, I can approve only, first of all, the high professionalism of SLB, deep expertise of your team in geomechanics, and first of all, a huge impact for the drilling optimization, well construction, and etc. Yeah, it's very important. And as I mentioned, and Ms. Clairet, Mr. Robert discussed with you that the main goal today represent geomechanic advantages today. It's about how we can get additional benefits from these technologies for growing Ukrainian oil and gas centers and industry. Sorry. Unfortunately, today, Ukrainian company doesn't use fully this technology. And one of our tasks in SPE society to develop as much as possible, thanks also to you, this technology and other technology. So in general, thank you so much that you have found the time individually. I know that you're very busy and you have a lot of projects, not only in Ukraine, but also outside of Ukraine. Thank you so much. Unfortunately, Russian Federation didn't allow us to be more with you and discuss Q&A session. So if you have time more, you can be here with us for the next some minutes. If not, we will be able and we will be appreciated if maybe you will answer for our question.
Yeah, we will stay. We will stay as long as necessary. Also, I left a comment in the chat that you can contact us anytime, either directly or through Maxim.
Up to you. Up to you. Thank you so much. Thank you so much.
Thank you all.
Thank you.
Thank you. Thank you, colleagues. Thank you, SLB team, for a nice presentation and for your great job in geomechanics and other streams. Dear colleagues, we have one more presentation. From this point, I will be switch into Ukrainian. Шановні колеги, у нас є ще одна цікава презентація. Якщо у кого є ще час, орієнтовно хвилин 15, то я запрошую на дану сцену Олександра Архіпова, менеджера з інновацій в бурінні інженерно-технологічного центру, який відповідає в частині буріння за впровадження технології геомеханіки. Олександре, будь ласка, вам слово.
Так, дякую. Зараз перевіримо. First of all, I'd like to thank you, Claire and Robert, for a really great presentation. Let us just try to share my presentation that will be focused more on practical application of the geomechanical modeling, mostly in Drugin. Thank you, Robert, for adding valuable information regarding advantages of geomechanical modeling in Stimulation. That is rather important, especially in unconventional reservoir development. But if you excuse me, I will switch to Ukrainian to quickly cover our detect oil and gas experience with geomechanical modeling. And I hope to take maybe a few minutes, but let's see if it works. Yeah, it works. I will proceed and then we can, if you have time, we'll have a Q&A. Так, колеги, перейду на українську. Так, а чи не можна забрати цей зміст на 3 полосочки зліва натиснути? Бачите? О, супер. Так, дякую. Почнемо з того, що геомеханіка, чим вона важлива нам для буровиків при споруджуванні свердловин. Вона дозволяє зняти багато невизначеності, оскільки підземні умови постійно з цим пов'язані. Ми, на жаль, не можемо, геофізичними методами можемо трохи заглянути в свердловину, але насправді ми бачимо тільки один шматочок одного розрізу, однієї свердловини. І як попередні доповідачі Шумберже показували, дуже часто важливо дивитися на картинку в 3D, тобто враховувати впливи від розломних порушень, від соляних штоків. І все це моделювання дозволяє нам визначити стабільне вікно безпеки для буріння. Тобто буде у нас за низький гідростатичний тиск бурового розчину. Це, як бачите, призведе до обвалів, до суттєвих обвалів. Буде забагато, почнемо отримувати поглинання, прихоплення, спровокуємо гідророзрив порід, теж недобре. Тобто не зможемо досягти цілей буріння. Тобто геомеханіка дозволяє нам знайти не просто це вікно стабільності, а ще врахувати ціль, для чого ми буримо. Ми ж хочемо видобути вуглеводні, тобто завдати якнайменшої шкоди колектору. Тобто це такий собі пошук такого компромісного сценарію, при якому ви допускаєте деяку нестабільність ствола, не доводите до поглинань, щоб не забруднити колектор, але при цьому тримаєте контрольовано, спостерігаєте постійно за цими проявами нестабільності ствола для того, щоб попередити поступлення якоїсь великої аварії. Конкретно на цьому слайді ще прошу звернути увагу на методику так званого подовженого тесту на приймальність, extended Guikov test, який зачасту в бурінні на практиці зупиняється просто на звичайному жовта точка. Не впевнений, чи... тут лазерної указки немає, так? Да, якщо можна. Є щось? Ні? Так. На жаль, нічого не видно. Так, добре. Жовтенька точка на графіку Guikov. Тобто зазвичай проводять з-під башмака опресування цементного кільця і тільки вже при відхиленні від прямолінійного тренду зупиняються. Але зверніть увагу, де ця точка в фактичному моделюванні знаходиться. Вона знаходиться між мінімальним напруженням мінімальним горизонтальним напруженням в цій зоні та розривом суцільних порід, брейкдауном. Тобто діапазон може бути досить широкий і на практиці вам нічого не скаже. І ви, можливо, зробили опресування в цільній породі, яка не має тріщини. Думаєте, що у вас досить широке вікно по буровому розчину, у вас є запас на прийняття великої пачки при ГНВП, у вас є запас, куди обважнитися. Але насправді потім якась прикра ситуація відбудеться, може запаковка шламом, ви створите примусово тріщину в породі, зорієнтовану в напрямку найбільш вигідному для того, щоб при найменших тисках розвиватися, тобто у напрямку максимального стреса, розсовуючи таким чином мінімальні горизонтальні напруження. І різко виявиться, що у вас під башамком тримає не 2.0, а всього-навсього 1.55. При тому, що Гіков ви спокійно отримали 2.0, і ніби падіння тиску не було, все чітко. І це може бути такою несподіванкою, що, скажімо так, може зупинити просто проект буріння, ви не досягнете цілої мети. Звісно, наперед знати всього цього неможливо, і для того і важливе геомеханічне моделювання, щоб врахувати всі ці спостереження, які ми отримуємо з результатів буріння, з геофізичних даних. Так. Перепрошую, на жаль, ця штука не працює зовсім. Зараз, секундочку. Є. Так. Для прикладу, повернемося до питань зменшення до невизначеності. На даному слайді розглянемо ситуацію поглинання. І ви ніби отримуєте результат. Тобто у вас зараз є якась певна густина бурового розчину, ви спостерігаєте, скажімо, часткові поглинання, з перерахунку ви отримали якесь значення вибійного тиску, бо еквівалентної густини вибійної. І питання ж тоді, а куди ж розчин приймає? І подивіться, наскільки багато можливих сценаріїв, що може відбуватися. Починаючи зліва направо, це може бути приймальність в дуже пористий колектор, тобто або такий, що має пустоти в собі. При тисках, будь-яких тисках вище пластового будуть спостерігатися поглинання, поки ви їх не заблокуєте, цю фільтрацію не зупините. Далі синя лінія – це якраз тріщина, яка існуюча, або ви її раптово створили, зорієнтована в напрямку максимальних напружень, яка потребує найменшої величини тиску, щоб призводити до її розвитку, до розкриття, і це фактично вже можуть бути катастрофічні поглинання, тобто ви закачуєте, як в режимі ГРП, ваш буровий розчин. Трохи далі, червона лінія, у вас може бути така якась діагональна, трохи не зорієнтована у вигідному напрямку тріщина, але вона є, вона проникна, і вона буде приймати десь посередині. І найгірший варіант, просто щоб показати, що таке теоретичний сценарій, який моделювання дозволяє покрити. Наприклад, жовта лінія, вона показує overburden стрес, тобто фактично треба підняти всю породу, яка знаходиться над, тобто бачите, тріщина є горизонтальною, і треба підняти всю породу догори, щоб створити тріщину в цьому напрямку. Такий режим в деяких умовах, особливо гірських, може бути якраз і основним режимом поглинання. Інші питання, на які допомагає відповісти геомеханіка. Ось для прикладу, це фрагмент вже готової 1D геомеханічної моделі, і справа в кружечком введено каверномір. Тобто ми бачимо ствол, номінал над і під якоюсь аномальною зоною. І питання ж тоді постає, що це таке? Це в нас, можливо, перевищили літраж в цьому місці, третій насос запустили і відбувся розмив ствола, або осипання. Можливо, зафіксували вимив якоїсь породи. Наскільки проблематична ця ситуація була? Чи треба з нею боротися? Якими заходами? Тобто збільшувати густину чи залишатися як є? На подібного роду питання дозволяє відповісти геомеханіка. Інший варіант застосування геомеханічного моделювання – це розгляд і агрегації даних історичних з попередніх результатів буріння. Наприклад, модель, яку ви зараз бачите, фрагмент, тобто була зібрана інформація там близько з десятка свердловин від дуже старих до трохи новіших, з різною точністю, свердловини різної конструкції, але все це дозволило створити попередню модель для нової проектної свердловини. І як бачите, прошу звернути увагу на відмінність від попередніх моделей, які я показував, дана має таку штриховку, тобто вона враховує вірогідність розподілу значень. Тобто ми закладаємо цю невизначеність уже на етапі моделювання. Тобто звужуємо собі дещо вікно для роботи, але таким чином попереджуємо можливі проблеми при бурінні. А також цей метод дозволяє зоптимізувати конструкцію свердловин вже на підході до нашої першої свердловини. Тобто вже плануємо на успіх, а не закладаємо якийсь цикл кривої навчання з помилками. І щоб завершити, приклад, до чого призвело на одному з наших родовищ геомеханічне моделювання, на якому ми почали з першої ж свердловини. Ми врахували історичні дані, проводку робили придріл та поздріл всіх наступних свердловин, і зверніть увагу, як у нас ми почали випробовувати межі згідно даних, які отримали за геомеханічним моделюванням. Тобто спробували підняти одну колону трохи вище. На наступному етапі спробували іще підняти цю колону і підняти, відповідно, ще одну колону. І фінальним результатом всього цього, маючи тільки вертикальні свердловини, ну, нехай там, можливо, з невеликим S-подібним відходом деякі, але фактично вертикальні в секції продуктивній, ми змогли пробурити найглибшу горизонтальну свердловину успішно з першого разу, при тому, що взагалі світовим трендом вважається: буріть вертикально, потім градусів 20, 30, 45, пробуйте, дивіться, як воно йде, і тільки тоді виходьте на горизонталь. Незважаючи на всі трудозатрати фінансові та людські, щоб створити це моделювання, фактично було зекономлено декілька свердловин, щоб реалізувати цей амбіційний проект з першого разу і без аварійних випадків. Дякую. І якщо у наших колег з СЛБ ще буде можливість, спробуємо якийсь Q&A зробити. Максиме?
Так, Олександре, я дуже вам дякую за змістовну і практичну і таймінг доповідь. Наша зустріч називалася «Геомеханіка від теорії до практики». Шановні колеги, на жаль, ми вичерпали час для офіційної частини, враховуючи повітряну тривогу. Тим не менш, ті колеги, які зараз офлайн, можуть продовжити спілкування і з Олександром, і між собою в приємній атмосфері за підтримки спонсорства компанії SLB. Так, дякуємо ще раз компанії SLB, пану Євгену Вішнікіну, директору SLB Ukraine, для того, щоб говорити і питання геомеханіки, і інші можливі колаборації в рамках SPE спільноти. Колеги онлайн, а також інші колеги, якщо у вас є запитання, ми їх акумулюємо і направимо нашим експертам безпосередньо для відповіді. Шановні колеги, ще раз вас прошу донатити. Наші колеги оргчарту виведуть на екран QR-код всі ми зараз можемо далі займатися, в тому числі нафтою і газою, завдяки нашим Збройним силам і всім іншим, хто допомагає, підтримує Україну задля перемоги. Будь ласка, зі своєї сторони хотів би подякувати ще раз менеджменту Полтавської політехніки, яка вкотре дає можливість проводити такі заходи, класно технічно організовані, за участю інших експертів в своїх стінах. Дякуємо вам за підтримку і дякую своїй команді і іншим колегам за те, що посприяли організації. Колеги, всім дякую вам за участь, дякуємо, що доєдналися. Welcome, як то кажуть, до SPE спільноти. Гарного і тихого вам вечора. А на цьому ми будемо офіційну частину нашу закінчувати. Пане Олександре, далі, будь ласка, модеруйте вже частину позаофіційної для продовження. Шановні колеги, дуже всім дякую. До нових зустрічей.
Дякую, Максим. Thank you once again, Clairet and Robert, if you're still hearing us.
Yep, thank you.
We're here.
Thank you so much that you also with us.
Sure.
Due to the time limit, we'll have to cut the event, but we'll be here and continue our discussion here. Like we also have SLB representatives. So yeah, any questions to SLB will be forwarded through your team. Many thanks once again for
Thank you very much.
your time.
Thank you. Bye-bye.
Yeah, thank
Stay
you.
healthy.
Bye-bye.
Keep in touch. Bye-bye.
Thanks.
Шановні колеги,
safe.
до побачення. Thank you so much. Thank you so much.